our invited speaker, Professor Mahesh Kakde from IISc Bangalore, and he will start this session by his talk on Hilbert's 12th problem and Stark conjectures. So, Professor Kakde, you may please start your talk now.
Okay, thank you. Can everyone hear me?
Yes, I
yes, yes,
so, yeah, all right. Thank you. Thank you for the opportunity to speak here in these unusual times. So I hope we all get through these bleak times, all right, and have a real math conference with in person soon. Okay, so I'll talk about my recent work on Hilbert's 12th problem and Stark conjectures. Okay, so let me begin by a very classical result about abelian extensions of Q. So firstly, we all learn in first course on Galois theory that if n is a natural number and zeta, if I denote zeta n by the for the nth root of 1, then the Galois group of the extension Q zeta n over Q is Z mod nz cross. Okay. So this is one of the Galois groups we compute in the Galois theory course. So this is easy, but on the other hand, there's a remarkable result that of Kronecker-Weber from 19th century, which says that if you take any abelian extension of Q, then it is in fact contained in one of the cyclotomic extensions. Okay, so there is a positive integer n such that K is contained in Q zeta n. Another way of saying this is that the maximal abelian extension of Q, Q ab, is union of all the cyclotomic extensions. Okay, so this is a 19th century theorem. Kronecker first stated it in 1850s, and Weber gave a proof in 1880s, which had a flaw, which was discovered nearly 100 years later. And the first correct proof, as far as we know, is due to Hilbert from 1890s. Okay, this is called Kronecker-Weber theorem. Okay, but the upshot of this is that all abelian extensions of Q are generated by values of analytic functions at rational numbers. So the function is e to the power 2 pi I x. Okay, so if you put x equal to a rational number, you get a root of unity, and you adjoin all those values, and you get abelian extension of Q. Okay. Okay, why does this? Okay. Another example of this sort is again a theorem that began in that's from 19th century. So if you take imaginary quadratic field Q square root of minus d, where d is a positive square free integer, then you can we know how to explicitly get the maximal abelian extension of f. Okay, so what you do is you take you take an elliptic curve with complex multiplication by the ring of integers of f. Such a thing always exists, not necessarily over Q, but over what is called the Hilbert class field of f. Okay, and you take the j invariant, the j function, which is the modular form, the well-known modular form G2 cube divided by delta, scaled appropriately, so by 1728. So you take this j function and evaluate it at E. So that's one thing you adjoin to f, and the other things you adjoin are values of what are called Weber function at torsion points of E. Okay, so so E is an elliptic curve. It has a group structure, and you take the torsion points of E and torsion points, and you evaluate the Weber function at these torsion points, and you get abelian extensions of f, and you get all abelian extensions like this. So again, this was this goes back to Eisenstein, Kronecker, and so on. A lot of people contributed, and I think it was finally completely settled by Takagi in the early 20th century, so 1920s. Okay. A remark that I would like to make here is that Q and imaginary quadratic fields are the only number fields which have finitely many global units. Okay, if you take any other number field, the group of global units, as we learn in Dirichlet's unit theorem, is infinite. So, so somehow when you have infinitely many global units, that causes a lot of difficulty, it seems, in the questions that we are going to address in this talk. Okay, I don't know exactly why, but this is what happens. Okay. Okay. So Hilbert's 12th problem, what is it? So in his ICM talk in 1900 in Paris, Hilbert uh, listed 23 problems, and the 12th of these problems was generalizing the Kronecker-Weber theorem and the theorem of complex multiplication for imaginary quadratic field to any number field. So he says, finally, the extension of Kronecker's theorem to the case that in place of the realm of rational numbers or of imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. Okay, so that's what Hilbert wrote about this problem, um, and it's there are many attempts to do this. Okay, so one of the attempts is through Stark's conjectures. Okay. So there's a partial result in this direction from the second half of 20th century, 1950s, 1960s. So let me recall that. So F is called a totally real field if all its embeddings into C are actually contained in R. So for instance, a real quadratic field, which you get by joining square root of a positive square free integer. Okay. So that's a totally real field, just what you would imagine it to be. And a CM field is a totally imaginary quadratic extension of a totally real field. So what you do is you take a totally odd, totally negative element of a totally real field. So you have all the embeddings of your field F into R. So and you take an element of F such that in each embedding it's a negative element. So that's a totally odd element, and you adjoin its square root. So that gives you a CM field. Okay, so these are all the CM fields. Okay, then Shimura Taniyama, using their theory of complex multiplication, they constructed abelian extensions of CM fields. So just like in the case of imaginary quadratic field, where you used elliptic curve, they used abelian varieties with complex multiplication. Okay, and then you adjoin what is called a moduli, so that kind of replaces G of E, and then you adjoin all the torsion points of these abelian varieties in some way, and you get abelian extensions of K. Okay, unfortunately, unlike the case of imaginary quadratic field, in general, you don't get all the abelian extensions of K. Okay, in fact, you can show precisely the extensions which you cannot get. This was proved by a student of Milne in 1970s, I think, that the extensions that Shimura and Taniyama miss out are precisely the extensions coming from the maximal totally real subfield of K. Okay, so and this is the topic of my talk today: how to get abelian extensions of totally real fields. Okay, so what I'm going to talk about complements this theory of complex multiplication. Okay. All right. So Stark's conjectures. Okay. So Stark made in a series of papers in 1970s. at least 4 in advances of mathematics. He made many conjectures where he proposed existence of certain special elements, which we now call Stark units, which are related to the leading term of L functions of f, okay, Artin L-functions of f, at s equal to 0 or at s equal to 1. Okay. Um, so at first, Stark's motivation was to, so you take this Dirichlet's class number formula, which gives you the leading term of the Dedekind zeta function at s equal to 0, and it gives a formula for that in terms of the class number, a regulator, and the number of roots of unity in that field. Now, Dirichlet zeta function using Artin formalism, it decomposes as product of other L functions, and he wanted to decompose the other side of the equation also um, uh, into some factors so that the factors match up. Um, but then, so he proposed existence of certain units in that factorization so that the factors match up. But it turned out that these Stark units actually generate abelian extensions of number fields. So that was quite amazing that you could generalize two very classical 19th century things. So you could generalize Kronecker-Weber and you could generalize Dirichlet's class number formula using these conjectures that Stark made. Okay, so a canonical reference for reading about Stark's conjectures is a book of Tate. By the name of Stark's conjecture. Okay, so he not only sort of gave a very nice exposition of these conjectures, he made them more precise. He related it to a conjecture of Brumer. That's the first place where sort of the relation appears explicitly, though I guess people knew about this all along. Okay. Okay. So along the same line, so Gross gave a p-adic refinement of these conjectures using p-adic L-functions. So he used p-adic L-functions to refine these conjectures. And then finally, sort of about 15 years ago, my collaborator Samit Dasgupta, he refined conjectures of Gross and proposed a precise p-adic analytic formula for these so-called Brumer-Stark units. Okay, so as we'll soon see, Stark conjectures, they postulate, I mean, they postulate existence of certain elements, but they don't tell you exactly how to construct one, even if you know their existence. Dasgupta's conjecture actually gives you a formula if you can prove the conjecture. Okay, so here's the setup. Okay, so again, F is a totally real field. H is a CM abelian extension of F, but need not be quadratic. Okay, H over F need not be quadratic. It could be a bigger extension, but it's abelian and finite. And I denote by G the Galois group of H over F. And S is the set of primes that ramify in H. Okay, precisely the set of primes that ramify in H. Okay, throughout my talk, I'll not have infinite places. Okay, so otherwise I should ideally put infinite places in the set S. Okay, so for any character of G, I can find it's finite order because it's for a finite group. For any character of G, I define the L function this way, as usual, by Dirichlet series. It also has an Euler product like this. Okay, so a priori this makes sense for real part of S bigger than 1. But as we all know, this has a meromorphic continuation to the whole complex plane minus 1. And also at 1 if chi is not the identity character, and which it won't be because I assume chi is odd. So it has a analytic continuation to C. Okay, and I modify it in a certain way. So this last line is perhaps not that familiar. So I multiplied by these finitely many factors, 1 minus chi of L, norm of L to the 1 minus S. Okay, so this makes everything integral. Otherwise, we have to deal with denominators and we can't make integral theory. So this thing has some significance, but it doesn't matter what non-empty finite set T we choose. It just has to be large enough and disjoint from S, and things work. Okay. All right. So, oops, sorry. Okay. So Stickelberger element. Okay. I can put all these L functions evaluated at 0 together and make a group ring element. Okay. So CG is the group ring with complex coefficient and on the group ring G. Okay. So theta is the element that, so it's a group ring element. So I can evaluate it at any character chi of G, and I get this LST chi inverse comma 0 out of it. Okay. Yeah. Okay, I just realized a typo, but I'll come to that later. Okay, so this is these E chi are the idempotents. Okay, the group ring idempotents. Okay. So a priori, this has complex coefficients, but a sort of celebrated theorem of Ziegel and Klingen and Shintani, so they proved this fact independently, the three of them, says that this theta in fact has coefficients in Q. Okay, so it belongs to the group ring over Q. For this theorem of Ziegel, Klingen, and Shintani, you don't need this set T. As you see, T is kind of almost a rational number, right? It's an algebraic number, and so you don't need it. You can divide by that thing. It's a non-zero algebraic number, and you can divide by it, and you still have this theorem. The T is needed for the next theorem, which is a refinement of the first theorem proven independently by Deligne-Ribet and Cassavetes. It says that this theta, St, so T is important here, is actually an element in Zg, not just in Qg, but it has coefficients in integers. Okay, all right. Okay, so that this is an important object for us. Okay, so this theta you should think of just as some kind of L function, but a group ring valued L function rather than L value actually, because I have already evaluated at S equal to 0. So you should think of it as an L group ring valued L value. Okay, so that's one side, right, in all for my results. The other side is some kind of arithmetic objects. Okay, so on one side I have some analytic object, and on the other side I have some arithmetic object. Okay, all right. So what's the arithmetic object? Well, the arithmetic object that I have for stating this conjecture of Brumer and Stark is the class group. Okay. So what kind of class group do I take? Well, I don't take the usual class group. I take something slightly bigger. So I take the T smoothened version of it, right? So I have this set T on the analytic side. So I should have it also on the arithmetic side. So what I do is I take the quotient of all the fractional ideals of H, which are co-prime to S union T, by principal fractional ideals. So if I just stop there, I would get the usual class group. But I only take principal fractional ideals which have a generator congruent to 1 mod every element of T, 1 mod every prime in T. Okay. So if you like, an alternate way of saying this is you take the Galois group of the maximal abelian extension of H, which is unramified outside T, and at T it's at most tamely ramified. Okay, so you allow some ramification. If you take the ideal class group, you have unramified, everywhere unramified extension. But in this T smoothen thing, you allow tame ramification at primes in T. Okay, so it's slightly bigger. Okay. So what does the Brumer-Stark conjecture say? So this was Brumer never. So this is the version that Brumer is due to Brumer. He never wrote it down, as I learned while writing this paper, but he gave lectures on this. So one of his student Rideout, he wrote a version in his thesis in a special case, and he proved weak results towards it. That was his PhD thesis. So this version is due to Brumer. It says that the Stickelberger element annihilates the class group. Okay, so the Galois group of H over F acts on the class group, and so ZG acts on it, and you can talk about annihilators inside ZG, and the Stickelberger element annihilates it. Okay. Now, why is it called Stickelberger? Because there is a classical theorem of Stickelberger from 1890, which is precisely this result when F is equal to Q. Okay. So Brumer's conjecture was an attempt to generalize Stickelberger's theorem from Q to any totally real field. Okay. So what do we know about this Brumer-Stark conjecture? It was more or less completely open until recently. So there were some cases known due to, so Wiles had this ingenious horizontal Iwasawa theory argument, which leads to proof of this Brumer-Stark conjecture for so-called nice extensions, but that's quite restrictive. Okay, so the result, so the main theorem of today, but I'll not talk about its proof except very, very briefly at the end, is that Brumer-Stark conjecture holds up to 2 part. Okay, so this is a conjecture over Z. We cannot prove it over Z. We can prove it once you invert 2. Okay, so up to sort of 2 part of the class group, theta annihilates the class group. Okay. In fact, we prove a stronger version. So this fit is the fitting ideal, and fitting ideal is contained in annihilator ideal. So fitting ideal is a smaller ideal, which means that we prove something stronger about theta. So yeah, there is a typo. There should be H over F here, and there should be some decoration pound here. Yeah, so that's the typo I was referring to because of the way I defined theta. But this theta belongs to the fitting ideal. Now I don't take the class group itself. I have to take this V, which is the Pontryagin dual of the class group, and I have to take the minus part of it. But that's okay because theta is 0 on the plus part, so it doesn't matter. And because I have inverted 2, I can take the minus part. To take the minus part means complex conjugation of H over F acts as -1. Okay. So if you don't, I mean, you can just think about the annihilation statement if you are not familiar with the fitting ideals, but the proof has to go through a stronger version somehow. We can't just prove the annihilation statement, as I'll say at the end. Okay. So that's the result. And in fact, one of the main obstructions in proving this at 2 is we don't know precisely what this stronger statement should be in terms of fitting ideals. So that's one of the obstructions why our proof doesn't yet work for p equal to 2. Okay, so at 2. All right, so that's the Brumer part of the Brumer-Stark conjecture. I should also tell you what the Stark part is. Okay, so an equivalent statement. Okay, so what these conjectures of Stark always depend on choosing a place of F that splits completely in H. Okay, the place could be a finite place. The place could be an Archimedean place, an infinite place. For me, in this talk, it's going to be a finite place. So I take a prime P of F that splits completely in H. Remember, H over F is a finite extension. F is totally real. H is CM. And I take a prime in the ground field that splits completely in H. I fix a prime in H above it. So these things will depend on this choice of the prime, but they are all equivalent if you choose a different one, quite trivially. Okay. Then Brumer-Stark conjecture is equivalent to existence of certain P unit. Okay, so these are, even though they are called units, they are not really global units. They are P units. So they are units away from P. So Brumer-Stark conjecture is equivalent to existence of a P unit U, which is congruent to 1 mod T, and it is related to the Stickelberger element theta in this particular way. Okay, so if I take odd of sigma u scale, and then sigma is the element of the Galois group. Okay, so this odd is the p-adic odd, right? The usual sort of p-adic odd. So this is an integer, and if I stick this integer in front of this element of the Galois group, I get an element in Zg. Okay, so this sum is an element in Zg, and the statement says that there exists a u such that when you make this construction, you get your theta. Okay, so it means that this equivalent statement gives you L value using odd of sigma u. Okay, so this, or another, or the other way of seeing this is that it gives you the formula for odd of sigma u in terms of L values, right? Because this theta was defined in terms of L values. Okay, so to go from one to other is slightly tricky because you have to use this partial zeta functions. Okay, but you can write partial zeta functions in terms of L functions and L functions in terms of partial zeta functions. So it's all the same. Okay, so so how do we get this equivalence? Well, I'll not tell you how to go from this statement to the other one, but I'll tell you how to go from the other statement to this one. So you have the annihilation statement. Okay, so theta annihilates some class group. So what I do is I take this P, capital P, in the ideal of H, and I look at its class in the T-smoothed class group, the CLT. Okay. Now, if I let theta act on it, that annihilates it. Okay, so I get the trivial class, and trivial class is by definition, it means that I get a principal fractional ideal. Okay, so I get this U. Okay, which is congruent to 1 mod T and so on. So that's the U that I want. Okay, just by definition. Okay, so that's how you go from the annihilation statement to existence of this Brumer-Stark unit. So I'll call this the Brumer-Stark unit. Okay, so the theorem that I stated on the previous page, it says that this U exists up to taking 2 powers. Okay, I may have to take 2 powers to because I don't have the theorem at p equal to 2. All right. Okay, so there's a higher rank version of this, where instead of just taking 1 prime, you take R distinct primes that split completely in H. And this leads to what is called the Rubin-Brumer-Stark element. Okay, that lives in, so it doesn't quite, it's not quite in H, it's what called the Rubin lattice. Okay, so in the end, I'll mention this once. So here's the remark. But if you like, you can just think about rank 1 case. Okay, so what's the application to Hilbert's 12th problem? Let me quickly say this. So what I do is I take an integral ideal f of my totally real field f, and I choose a prime p which is co-prime to this integral ideal f, and I let H be the maximal abelian CM extension of f of conductor this math frac f, okay, in which p splits completely. So sometimes I call this Gross-Stark unit, but I meant here Brumer-Stark unit. Okay. So then there's this Brumer-Stark unit UF comma P, and one can show that that unit actually generates H. So H is F adjoint this unit. Okay. Now if I vary my F and if I vary my P over all possible choices, I almost get F ab, but not quite. There's issue of some signs. What I get is the maximal abelian CM extension of F. Okay, and now to pass from maximal abelian CM extension to the maximal abelian extension, I have to adjoin some square roots. So square roots of the signs. Okay, so so all these Brumer-Stark units. So remember, I'm just using the rank 1 case here. And that's why I did not state the higher rank case precisely. So Just using the rank 1 case, I get all, I get the maximal abelian extension of F. Okay. But remember, Brumer-Stark conjecture only gives me a formula for odd of these units. Okay. So our theorem only gives the formula for odd of these units. It doesn't tell me how to construct these units. So this is not quite what Hilbert asked for, because we want an explicit construction of these units. Now we know that they exist. We don't know how to construct one. So if I give you F, if I give you math frac F and P, then I can tell you that this UF comma P exists. But Brumer-Stark conjecture doesn't tell me how to construct this U. So it doesn't give me a formula for it. Okay, so in 1980s, Gross gave some refinements of this. So starting with Gross-Stark conjecture and what is called the Tower of Field conjecture. So it gives us more information about these units. It still doesn't tell me exactly how to construct it. And that exact formula for these Brumer-Stark units was conjectured by my collaborator Samit Dasgupta. Okay, so I'll come to that in a minute. Okay, so let me come to the p-adic refinement by Gross. Okay, so remember, F is my totally real number field. H is a finite abelian CM extension still, and chi is a totally odd character of G, which is the Galois group of H over F. Okay, so this theorem of Deligne, Ribet, and Castelnuogas that I mentioned earlier, in fact, it gives me a p-adic analytic function, the p-adic L-function as it's called, p-adic L-function LP, from ZP to CP. Okay, so from p-adic integers to the completion of QP bar, such that it interpolates these L values. Okay, these are the classical, so the right hand side here is the complex L function as defined earlier. And my p-adic L function, when I evaluate it at S equal to a negative integer congruent to 1 mod p minus 1, I get this. Okay, usually it's sort of odd negative integers, but then you have some powers of this Teichmüller character omega coming in here, which I did not want to mention. So this omega on the left hand side you can just think of as notation. Okay, this determines it uniquely, so it doesn't matter if I tell you its values at more integers, it's still the same function. Okay, but for this I must say that S should contain all primes above P now. Okay, so now S means something slightly different than before. So S was precisely the set of primes of F which ramify in H, but now in addition they contain all primes above P in F. Okay, so Gross made two conjectures about this. One was about the order of so here this S, remember the definition of L function. So you remove all Euler factors at primes in S. And so in fact, you can show that whenever there is a prime above P that splits in H, so chi of P is 1, this L function is 0 at S equal to 0. Okay, so it's easy to show that whenever you have a prime like this, so whenever R is bigger than or equal to 1, LP chi omega 0 is 0. Anything finer is much harder to say. Okay, so Gross conjectured that the order of vanishing of this L function, p-adic L function at 0 is precisely R. Okay, it's precisely the number of primes such that chi of P is 1. So this part 1 is completely open. We know that this order is greater than or equal to R, as I'll say on the next page. Okay, let me come to that a little later. He went further and he gave a precise formula for the leading term. So rth derivative in terms of what is called gross regulator that I'll define, and then there are some factors that you have to put in, some correction things. Okay, so not only did he conjecture about order of vanishing of this L function, he gave a precise formula for the leading term. Okay, so what do we know about this conjecture? So about order of vanishing, we know that it's at least R. So when R is 1, this is trivial, but when R is bigger than or equal to 2, this is quite non-trivial. So this follows from Weil's proof of the main conjecture, at least if P is bigger than 2. And then there's a completely analytic proof that's given by Dasgupta and Spies that works even for P equal to 2. Okay. So yesterday in Professor Balasubramanian's talk, we heard about this 6 exponential theorem and 4 exponential conjecture. And it seems that showing this precise equality is a transcendental problem of that nature. So I think if you can prove 4 exponential conjecture, the p-adic version of it, then you would get very close to proving this conjecture. Okay, so you get a weaker result about this using the 4 exponential theorem, using the 6 exponential theorem, or rather Waldschmidt's refinement of it. Okay, so that's what we know about the order of vanishing. And then about 2 years ago, I proved with Dasgupta and Ventulo the formula, the leading term formula. Okay, so part 2 is completely known. I must remark here that part 2 is independent of part 1, because I'm not saying leading term, I'm saying rth derivative. So if one is false, and in fact the order of vanishing is bigger than R, then we show that the right hand side is also 0. So we show 0 equal to 0. So that's the content if 1 is false, and that's also non-trivial to prove. And if 1 is true, you get the formula for the leading term. Okay. All right. So what's the regulator and what's the relation with more information about the Brumer-Stark unit? Okay, so definition, I don't know why the D became small. Sorry about that. So the definition of regulator is, I take this Rubin-Brumer-Stark element. You can think of this as wedge of R distinct units. They are actually not R distinct units. There are some small denominators, but you can, for the purpose of sort of getting the idea of how it's defined, you can just think of these as R distinct P units. And you take norm from FPI to QP. So this is a finite extension of QP. You take norm of UJ. So ith norm on jth element, and then you scale it appropriately by taking p-adic log. So this is an R by R matrix. I and J vary over from 1 to R. So this is an R by R matrix in general. And you take determinant of that. Okay, so that's the gross regulator that appears in the statement of Gross's conjecture, okay, or our theorem. All right. So what happens when R is 1? This is simply a number. There's no data. I mean, it's not a matrix. It's just a 1 by 1 matrix. And so you get a formula for this log T of norm of the Brumer-Stark unit. Okay, right? Because this thing is just a number now. I mean, this is just a summation of chi sigma inverse log P of norm of sigma U. And this is the L value, and this is some other thing. Oh yeah, I should also say that when R is 1, this order of vanishing is known. So it's exactly 1. And that's again something that was mentioned yesterday. That's the work of Baker, or rather p-adic refinement of Baker's result due to Brumer. Okay, so when R is 1, we know the precise order of vanishing, and that's a deep theorem of Brumer and Baker. Okay. Oops. I don't know what's happening here. Okay, so when R is 1, this conjecture of Gross gives a formula in terms of p-adic L-functions for log P of norm of sigma 1 U. Okay. sigma u1, sorry. So R is 1, so I can call u1 u. Log p is kind of harmless, so it gives a formula for norm of norm from fp1 to qp of sigma u1. Okay. So you get more information than just odd, right? Odd just tells you something about about the p-adic odd. Now you know what the norm is in qp. Okay, but of course this still loses a lot of information. One way to think about it is you're given a complex number and you're given just its absolute value. Okay, so so it loses a lot of information. So what's beyond Gross-Stark? Okay, if I want to go further, if I actually want the unit, what else can I say? Okay, so this u actually so it's in the p-adic completion of H, but because P splits completely, this p-adic completion of H is same as the p-adic completion of F. And again, I sometimes, I used to call it Gross-Stark unit, but recently I changed to calling it Brumer-Stark unit. And in some places it still says Gross-Stark, but they are used interchangeably by people. So depending on their point of view, if you come from the p-adic side, you call it Gross-Stark unit. If you come from the side of Stickelberger, then you call it Brumer-Stark unit. So this, you should read this Gross-Stark as just Brumer-Stark. Okay, so this Brumer-Stark unit, it it lives in H completed at capital P, but that's same as F completed at small p. Okay, so you can ask, what is, can you give a formula for this U in F completed at P? Okay, and more or less in his PhD thesis, Samit gave a formula for this. So he conjectured a formula for this Brumer-Stark unit as an element of this p-adic field. Okay, so as I mentioned earlier, if you prove this conjecture about the precise formula, you get Hilbert's 12th problem, okay, or p-adic solution to Hilbert's 12th problem. Hilbert stated it in a way like you need an analytic formula, and so one way to interpret this is as a p-adic analytic formula. Okay, so you get p-adic analytic formula for generators of abelian extensions of totally real fields. So this is my work in progress. So it's work in preparation, in fact. So we proved this conjecture of Dasgupta under very mild assumptions. So we have to stay away from finitely many p's, but that's enough for applications to Hilbert's 12th problem. Okay, so you can always stay away from a small finite set of primes for Hilbert's 12th problem. So that's beyond Gross-Stark. So so Gross-Stark tells you just what the norm is, and Dasgupta's conjecture tells you exactly what the unit is, and that's what we prove. Okay, so in the last couple of minutes, let me just say, give you a very brief sketch of how the proof of Brumer-Stark goes. Okay, so remember, I have to prove, so there should be HF here and the decoration hash. Okay, so this, which means that you invert, you send G to G, so summation AGG to summation AGG inverse, that kind of thing. But anyway, so I want to prove this inclusion. Now, so this is an ideal generated by theta in ZG. This is another ideal in ZG, or Z1 over 2G. This is also an ideal in Z1 over 2 G. Now I want to prove that this ideal, the left-hand side ideal, is contained in the right-hand side ideal. Okay. All the methods that we know using modular form only give you inclusion in the other direction. Okay, it will never give you inclusion in this direction directly. Unfortunately, this first inclusion can be strict. So there are many cases where the right-hand side will not be contained in the left-hand side. Okay, so this is not an equality. So remember, this is already a stronger form of Brumer-Stark conjecture. Now, you make an even stronger form of Brumer-Stark conjecture where you replace this theta by some variation. You replace this class group by some other variation. So these are called by tildes. And then you conjecture that the ideal generated by this theta tilde is same as the fitting ideal of this class group tilde. Okay. So and this statement should be strong enough to give you the first inclusion. Okay, so you have to come up with such a statement, and this was done by Kurihara and by David Burns and Popescu and so on. Unfortunately, we can't directly use their version, so we had to come up with our own version, which was slight variant of all those things. But that was strong enough for us to get the strong Brumer-Stark, get the first inclusion. Okay. Now, as I said, we can use modular forms to get that the fitting ideal is contained in the theta, in the L function, right? So we can always, I mean, the modular forms will always tell you that it will give you ways of constructing elements of. So this inclusion means that you have to construct lots of elements in the class group. Okay, and modular forms give you elements of constructing, gives you a way of constructing elements of the Galois cohomology. Okay, so this is due to, it goes back to Ribet in 1970s when he proved the converse to Herbrandt's theorem. So you use congruences between Eisenstein series and cusp forms to come up with elements in the Galois cohomology group. Okay, and this is a particularly difficult case because it's what is called P indistinguishable. So the eigenvalues of the Hecke, the roots of the Hecke polynomial at P, they are equal, and Ribet's method has never been used in this case before. So so in fact, this is a sort of novel refinement of Ribet's method that is used here. Okay, so we get this inclusion, and then we bootstrap this going back to our class number formula that I mentioned earlier to show that actually if you have this inequality in all cases for all intermediate extensions, then you actually get an equality. Okay, so you have to bootstrap this and get the equality. Once you have this equality, you can reduce the thing you want. Okay, so that's all. Thank you. If you have any questions.
Yeah, thank you, Professor Kakde. So there are some questions in the chat box.
So how do I see this?
Yeah, so yeah. So question from YouTube said, what is totally imaginary extension? I think missed it.
Oh yeah, so it is just, so totally real field means that all the embeddings into C, they land inside R, and totally imaginary means that all the embeddings into C are not contained in R at all. Yeah, so they also land outside R. So for example, if you take Q cube root of 2, then that's neither totally real nor totally imaginary, because there's one embedding that lands inside R and two embeddings that land that don't land inside R. But if you take Q square root of minus D, where D is positive square free, then that's totally imaginary because both embeddings land are not contained inside R.
So another question.
Oh, somebody already answered it actually. Yeah.
So another, so if all embeddings are non-real, yeah. And the last question. So are the Brumer-Stark units related to Ramachandra's units in the case of H mod A equal to imaginary quadratic extension of Q?
No, so these are, I mean, the Ramachandra units are related to what are called cyclotomic units. So those are on the plus side. So those are actual units actually, and these are P units. So they are not actual units. P units are somehow easier to construct in some sense than actual units. Like we don't know how to construct units. If you want to construct P units, philosophically, that's kind of easy. You just take you just take P and P bar and sort of take the ratio P over P bar. I mean, it may not be principal, so you raise it to high enough power, you get principal ideal. So you take P to the H divided by P bar to the H, and the generator of that is a P unit, and somehow that kind of thing works. So that's you should. I mean, so what I do is in some sense much easier than constructing these actual units.
I have a question.
Yes.
So when you defined that L function corresponding to number field,
Yes.
so their chi was a character on the Galois group.
Yeah.
So now in the L function you define chi of an ideal. So how are you looking at it?
You use class field. You use the Artin map there. You go from the ideal to the element of the Galois. Yes. So it uses something quite deep, and I kind of took it as standard that you get a element of the Galois group using the Artin map.
Okay.
I have another question.
Oh, yes. Hi, Gautam.
Oh, hi, Mahesh. How are you?
I'm fine, thanks.
So this goes back to very early stages of your talk when you talk about introduce the relevance of the Stark conjecture to Hilbert's 12th problem.
Yeah.
You've probably answered my question, but I have maybe not been able to decode what you said. So I'm talking about the Stark units, okay, not the Brumer-Stark units, but the Stark units.
Mm-hmm.
So the Stark units generate abelian extensions of number fields. But do we know what are the analytic functions of which the Stark units are values?
Yeah, so you kind of have to change. No, so we don't. You kind of have to change your point of view in some sense. That these are, I mean, Stark gives a formula for these units in terms of L values, L functions. And so in that sense, you get some analytic formula for these units. So you don't have one, unlike sort of imaginary quadratic fields or rational numbers, you don't have one function, one analytic function whose values will give you everything that you want.
Okay.
So you take these L functions. So you kind of, it may not be what Hilbert had in mind, but this is the best we can do at the moment.
I see. So Hilbert's 12th problem is almost like a tactically vague statement, and it's open to interpretation. Yeah.
Yes, and I think that's why he actually did not speak about it in ICM, though I think he thought of this as an important problem, and he worked on it quite a lot. As I said,
I see.
He gave a proof of his proof of Kronecker-Weber's theorem is the first sort of correct proof.
First correct proof.
No, and so I think there are problems which he spoke about it in ICM, and there are problems which he just wrote down, and this is one of the things he just wrote down because I think he couldn't make a precise statement. I suppose.
I see. Okay, thank you.
Is there any other questions?
I have a question. So about this p-adic analog of the Stark conjecture. Is that what is the shape of the conjecture look like? Like, do you have to choose a p stabilization, and then it's a conjecture about the L value?
P-adic Stark. I mean, this is the p-adic Stark conjecture.
No. I mean, in the last couple of slides, you mentioned that you're working on a p-adic analog of the construction of Brumer-Stark unit.
Oh, so you mean Dasgupta's conjecture, for example?
Yeah. Sure.
Yes. So, so you can think. I mean, so one way to think about this is p-adic L function is a measure on some on a global Galois group.
Yes.
So it's a so if P is inert in F, for example, then it's a measure on FP cross modulo closure of global units.
Okay.
Okay, that's the global Galois group in that. I mean, in the case of Gross-Stark conjecture. And what Dasgupta did was he lifted this measure from FP cross global closure of global units to FP cross.
Okay.
So he lifted this measure. Now this, I mean, unlike p-adic L-function, which is a well-defined function, this measure depends on lots of choices. Okay, there's no unique way of lifting it. But what he showed that its value, I mean, somehow when you integrate it against a particular function, just the identity function, it gives you a well-defined quantity. And that is what he conjectured to be the Brumer-Stark unit.
I see.
Okay,
So this is
so
is the analog of
that's how he removed the ambiguity that appears in Gross-Stark by lifting it.
I see.
Actually, it's a slight refinement of Gross-Stark, but yeah, he removed the ambiguity coming from the image of global units.
I see.
Yeah. And what you said about p stabilization is what sort of comes in the proof actually. So if you want using p-adic modular forms, yes, you have to work with p stabilizations of certain Eisenstein series.
I see. Okay. Thank you.
Yeah, any other questions? Yeah, it seems there is no other question. So thank you so much, Professor Kakde, for this wonderful talk.
Yeah, thank you for having me here.